All right, today we're going to be getting into curve sketching. So now, essentially, you have everything that you need to do, or you need to be able to do in order to do this appropriately. So curve sketching is really just figuring out how these graphs are going to look. So essentially, exactly what it says, sketching a curve, sketching a function, but we're going to use the properties of the original as well as the derivative as well as the second derivative to help us come up with a very appropriate graph for each situation. So my directions are going to stay the same the entire time. We're only going to look at 4 problems because these are very, very large problems where you are finding the first derivative, the second derivative, you are finding critical points, you're finding the concavity of each thing. So there's a lot to do with these things. So sketch the graph. Very simple, right? We're going to sketch the graph. We're not going to use a calculator though. Label any intercepts, relative extrema, and points of inflection and asymptotes. So what I like to do is look at my characteristics of the original function first, right? My original, I can get a y-intercept, right? So y of 0 would be 0 if I plug it in, which also tells me I have an x-intercept at 0, 0. So cool, 0, 0 is on my graph. Wonderful. I have no asymptotes, right? Because if I try to find when this cannot equal 0, this would give me imaginary asymptotes. So I don't need to worry about anything there. So pretty much I've extracted everything that I can extract from, oh, also horizontal, right? I have a horizontal asymptote at y equals 0 because I am bottom heavy. So now I for sure have extracted everything that I can possibly extract from my original function. So kind of cool that I'm going to pass through my horizontal asymptote. That just means that I can solve for where it's equal to 0. It's interesting. Do not let other teachers tell you that you cannot pass through asymptotes. You can't pass through vertical, and that's true. But horizontal just represents the end behavior. So I'm going to go ahead and look at my first derivative. So low d high minus high d low all over low squared. Right, low d high, yep, minus high, d low, yep. Okay, and this would simplify to negative x squared plus 1 over x squared plus 1 squared. So what I can use here, again, I'm not going to have anything where my denominator is equal to 0, still not going to be possible, but x equals plus or minus 1, those are going to be critical points. So if I test around those with my first derivative, right, relating my first derivative to my original function, I'm sorry, that should be y prime. So let's see, if I put in 0, that would come out positive. So I know I should be increasing there. If I put in a negative number, negative 2 would come out negative. And bigger would also come out negative because that negative x squared is much larger than 1. Okay, so I know I'm going decreasing to increasing to decreasing. All right, now let's see how we relate with y double prime. All right, and the other nice thing about this up here, right, is that I know that this is a min and this is a max because there's no points of discontinuity or anything. Right, so I could find my relative extrema at negative 1 by plugging negative 1 into my original function and seeing what the minimum is, and then putting in 1 to see what the maximum value is. Okay, so looking at our second derivative, so again, low d high. Well, I did it again, I done goofed. So here we go. Let's see if I can take the second derivative correctly this time. Hopefully, fingers crossed. All right, so I should be picking up where I left off, right? So I'm going to do the second derivative, so low d high minus high. I forgot that plus 1 last time. Ugh. High d low all that junk over low squared. Alright, so now let's see. We can divide out an x squared plus 1, at least one of them. So I can divide out this one that goes to 1, and this goes to 3. I will distribute everything in the numerator. So negative 2x to the third minus 2x. I'm going to rewrite this one just to save myself some grief and trying to think about how that multiplies out. All right, so now I will distribute my 4x to both of those. Go over the same denominator. All right, and then I will set it equal to 0 and go ahead and factor out a negative 2x. Actually, I'm just going to factor out 2x. So this will make it x squared minus 3. All right, let me make sure, because the numerator up here is essentially 2x cubed minus 6x. Yep, so factoring out 2x, x squared minus 3. Okay, so I have points of inflection, right, plus or minus root 3 and 0. So I have 0, negative root 3, positive root 3, and root 3 is 1.732. And I'm going to be relating y double prime to y. So if I put in a negative number, the denominator is always going to be positive because of that x squared. And then if I put in the numerator, negative 10 or something, I will have a negative times a positive. So this is a negative interval, which means I'm concave down. And then I will hit negative root 3. So I'm going to test negative 1, which would be a negative times a negative, would be concave up, and a positive interval. If I put in positive 1, that would be a positive times a negative, so a negative interval, which means I'm concave down. If I put in positive 10, that's going to be positive, so I'm concave up. So I have points of inflection at root 3, 0, and 3. And I need to find my max and min values. So I have negative 1 and 1 as my max and min. So y of negative 1 is negative 1 over 2 if I put in my original function. And y of 1 is 1 over 2 if I put in my original function. So negative 1, negative 1/2. So I'm right there. Positive 1, positive 1/2, right there. So let me, instead of using this graph on this one, I'm going to blow this up. Come on, make it straight. Ah, yeah. Come on. You can do it. Look at you. Look at you go. All right, this positive 1, negative 1, positive 1, oops, negative 1, positive 1, positive 2, negative 2. Right, so I have a horizontal asymptote at y equals 0. So I'm going towards that. I'm going to make it fat. All right, I know if I put in 0 to my function, it is at 0. And then I had negative 1, negative 1/2, so I'm in here. Positive 1, positive 1/2, so I'm up there. Points of inflection at my root 3 over 2's. So root 3 over 2, somewhere in here it's going to change concavity. And positive root 3 over 2, or sorry, positive root 3, I don't know why I'm saying root 2. So 1732, it's going to change concavity as well. So here I have a point of inflection. This is a point of inflection, y-intercept and x-intercept, and 0, which is an x-intercept, yeah. Here is a max. Here is a min. Here's a point of inflection. Okay, so for my graph, right, I'm concave down all throughout here. On the left side, as I'm going closer, let's make it green. All right, so that's got to be concave down, going close to the asymptote. And then I change and I'm concave up until I hit 0. So concave up until I hit 0. And then I go concave down until I hit root 3. So concave down until root 3. And then I go concave up from that point and beyond. So using my first derivative, my function, and my second derivative, I'm able to come up with a very good graph of what this should look like. I could figure out exactly where my points of inflection are if I wanted to. It would be root 3 over 4. But I'm not too terribly worried about it. So this gives a very good picture about where my maxes are, where my points of inflections are, where my mins are, where my intercepts are, where my horizontal asymptote is. Essentially, most of the things that I would want to know about this graph. So if I look at x plus x squared, x over x squared plus 1, so x divided by x squared plus 1, and I look at my graph, well, that's a pretty good picture there. Right, so I'm hitting at 1 and -1. I have my max. Right, here's my min at -1 and 1/2. Here's my max at 1 1/2. And 1.732 is somewhere around there, and it does look like it's changing concavity. As I go out forever, it's going to 0. So this paints a really good picture of everything that's going on with my graph. So using everything that we've done up to this point, this kind of helps me come up with good pictures of my functions. All right, now I think I'm okay on the rest of the video. I did make a mistake on number C, letter C, but I do fix it. So just pay attention on letter C. I make a mistake, and then I will fix it in the problem, I promise. All right, talk to y'all soon. Get our next one. So let's see. Just looking at it, this part is going to have some restrictions, right? X squared cannot be bigger than 9, so I'm only going to have things between 3 and -3 for this graph. So that's kind of restricting my domain there. For my x-intercept, I can set my function equal to 0. Right, so then that means x equals 0 is an x-intercept, which will also be my y-intercept, right? And then root 9 minus x squared equals 0. So x is equal to plus or minus 3. Those are also x-intercepts. So interesting graph here. I think it's going to be kind of like two semicircle type things, but I don't know. Let's find out. All right, so then let's do our derivative. So it's going to do the product rule. So the derivative of the first is just x, so just 1, plus the first times the derivative of the second, and then I'm going to get a common denominator with these things and combine them. Oh, and I need to multiply that 9 minus x squared by 2. All right, so again, getting common denominators here. This one's going to be over 2 root 9 minus x squared. So I need to multiply 2 root 9 minus x squared, top and bottom, right, in order to get a common denominator there. And then I just combine them into the same fraction. All right, so then I will combine a little bit more. So I would have negative 4x squared here, plus 18 over 2. Let's go ahead and divide out those 2's. Right, so just negative x squared plus 9. This 2 divides with both of those. So negative 2x squared, right? Yep, plus 9 over root 9 minus x squared. Interesting. All right, so now, right, x cannot be plus or minus 3, but those are already my endpoints, so I know I'm not differentiable there. I'm not going to worry about those so much. But if I solve for when it is equal to 0, that would give me 2x squared equals 9, so x squared equals plus or minus 3 over root 2. So let's think about 3 over root 2. Oops, I'm sorry, not x squared, just x. So this would be plus or minus 3 root 2 over 2. So 3 times 14 is 42, divided by 2 is 21, so this is approximately 2.1 something. So if I think about that on a number line, again, negative 3 to 3 are my boundaries for my domain, and I'm going to check around negative 2.1 and positive 2.1 to see the relationship with g prime and g. So if I put in negative 2.5 or something, let's see, the bottoms always has to be positive, so that's not going to be a concern. It's just going to be how it interacts with this negative 2x squared there, if it's bigger than or less than 9. So 3 squared is 9. So if I'm super close to 3, let's say it pretty much is 3, then that would mean this would become negative, because that negative 2 times a number close to 3 is going to be negative. So this will be decreasing. And then if I put in 0, that's a positive. Now it'll be increasing. This one will be decreasing for the same reason the other one was. All right, so what I was thinking in my head for that negative 2 times 2.9 negative, right? That's a number really close to 3. So if I assume that it is 3, then that's negative 2 times essentially 9 plus 9, which would be like negative 9 altogether. So that's how I'm getting negative for those intervals. All right, which also tells me that I have a min and I have a max. There's no points of discontinuity, so I know those are good. Alrighty. That's all I can tell from that. Alright, so let's do the second derivative. So low d high. Minus high d low. All over low squared. Yeah, okay. All right, so let's see. What I could do is get common denominators up top again. So that this will become, right, my common denominator is going to be this part right here. So I'm going to multiply that in to this one. So that will give me negative 4x 9 minus x squared minus 9 minus 2x squared times negative 2x. And then now what I can do with that root 9 minus x squared is I can put it into my denominator. So that's all dividing by it. So that would be a root 9 minus x squared to the third now. All right, and that makes my life a lot easier with the simplification of these things. So I'm going to go ahead and factor out a negative 2x because I see it here and I see it there. So negative 2x, and then this would be 2 times 9 minus x squared minus 9 plus 2x squared over this same junk. All right, so I have negative 2x times 18, so negative 2x squared. Well, that's convenient, right? It's just 18 minus 9. Right, that's what I'm seeing in my head. Those negative 2x squareds are going to make 0. So this is just 9 over the same junk. So really, all that I get out of this is x equals 0. And if I test around that 0, if I put in a negative, it's going to be positive. So g double prime would be positive here, which means I'm concave up. G double prime would be negative here, which means I'm concave down. And 0 is a point of inflection. Okay, so let's see. If I put in 3 over root 2 into my function, so g of 3 over root 2, let's see if I can get something that's reasonable. If I can't, I'm not going to worry so much about it. But let's see what we can do. All right, so that would be 9 over 2. So this would be 3 over root 2, root, because 9 minus 9 halves is 9 halves. So this is 9 over 4. 9 over 2, 9 over 2, 9 over root 4, which is 9 over 2. Right, because root 9 is 3, so 3 times 3 is 9. Root 2 times root 2 is just 2. So that's pretty much 4.5. So that's a nice number. All right, so I have negative 2.1 and 4.5. So somewhere right about there. And then if I put in negative root 3 over 2, that only affects my negative out front. So g of negative 3 over root 2 would just be negative 4.5. So I'm somewhere 1, 2, 3, 4. Somewhere right in there. And let's see, that's a minimum. A max. Did I mix my things up? What did I mess up, you guys? Oh, I put my spots in the wrong spot. I put my points. This is supposed to be over here. I'm sorry. And this is over here. I did it in the backwards order. Whoa. Whoa. All right, so 2.1, 4.5. 1, 2, 3, 4.5. Somewhere in there. I'm sorry. I did the positive one first, and then I did the negative one. I graphed them incorrectly. So now this is a minimum, and I am concave up until 0. So concave up until 0. And then once I hit 0, I'm concave down, and I have to be increasing. So interesting. That's just a weird looking graph. I don't know what to call that thing. But that would be our graph for the function, right? And if we typed it in, x root 9 minus x squared, let's see. Right? Hey, that's what we got. Look at that. Magic. Okay. So moral of the story, right? You can use the characteristics of the function, the first derivative and the second derivative, to help you come up with a very accurate graph. I mean, we pretty much nailed it. Yeah, some of the y values in between are probably a little bit off on our graph, but it gives a very good approximation of what we should be thinking about this function looks like. Okay, so I believe I only have two more for you guys, yeah. So let's see what we can do. So let's see, 5 to the t has a horizontal asymptote of 0, and 5 minus t does not have a horizontal asymptote. Yeah, as they go to infinity, well, let's find my zeros. All right, so 5 minus t equals 0. 5 to the t equals 0. Never! So t equals 5. 1, 2, 3, 4, 5. Boom! There's my first. And then if I find my y-intercept, g of 0, be 5 minus 0 times 5 to the 0. So that would just be 5. All right, that's all I can do right now. So let's go ahead and find my first derivative. So I need to use my product rule again. So this would be -1, 5 to the t, plus 5 minus t, ln of 5 times 5 to the t. So I'm going to factor out a 5 to the t. This is -1 plus 5 ln of 5 minus ln of 5t. All right, so that 5 to the t is never going to be 0. And then I can find where all that junk is equal to 0. So I'd add the 1, subtract the 5 ln 5. So t would be, well, I told you we weren't going to do this with a calculator, but I'm not sure of a good way to find that number without a calculator. I'm thinking. Ln of 5, that's a little bit bigger than 2. It's 1 minus 2 over ln 5. So I mean, it's going to be between 0 and -1. So what are we talking in terms of g prime? So let's just pick like -10 or something. So if I put -10 in, the nice thing about this 5 to the t is that's always going to come out positive. Even if I have a negative number for t, it's going to come out positive. It has to. And if I put in -10, that's going to make this a very large positive number. It would be 10 ln of 5, which this will come out positive, which means g is increasing. All right, and then if I put in 0, well, even if I put in like 50 or something, if I put in 50, then this is going to make this a very large negative number. So my interval should be negative, so I am decreasing there. So this will be a max where that is, which is somewhere a little less than 1. I don't know that it's going to be super useful to plug it in. It won't be. It's not going to be very pretty at all. All right. So this one we may use a calculator on a little bit. So let's see, for my second derivative, let's see what we can do. Which form would it be easier? Probably the form I have it in, huh? So if I do the derivative of the first, which is that 5 to the t, That would be ln of 5 times 5 to the t times all this junk. And then plus the first times the derivative of the second, which would just be negative ln of 5. Right, because that's just the power property right there. Nothing else is a t in it. So, all right. So from this point, I would probably factor out a ln of 5 and a 5 to the t. So I'm left with negative 1 plus 5 ln of 5 minus ln of 5t plus 1. So all that does for me is it makes those go to 0. So I have the place when the front here is never going to be 0, right? That's not going to be 0. It's not possible. So I have the position when ln of 5 minus ln of 5 times t equals 0. So if I subtract my 5 ln of 5 over, well, t has to be 5, right? In order for 5 ln of 5 minus a number times ln of 5 to be 0, that t has to be 5. So out at 5, that says g double prime or something like that. But at 5, so if I put in 0, that would be 1 times positive number, so this would be positive, which means I'm concave up. All right, does that make sense? If I put in something bigger, it's a positive times a negative, so I should be concave down. All right, I want to see what my y value is for g of my max. It has to be concave up. Guys, I can't do math. I was wondering why it wasn't making sense. I made 2 mistakes. I am so sorry. All right, so mistake number 1, I factored incorrectly on the second derivative, right? So I saw that they have ln of 5, 5 to the t, ln of 5, 5 to the t, but I missed my negative, which will carry down as that negative. So instead of t just being wonderfully nice and 5, I will have 5 ln of 5 minus 2 minus ln of 5t equals 0. So from this point, I would add the 2, subtract the 5 ln of 5. So t is 2 minus 5 ln of 5 divided by negative ln of 5. That's the mistake I made on the first one, right? So with this, when I was solving, I tried to solve too fast. I'm sorry. I really need to slow down when I'm doing these videos. But I forgot to divide by that negative, so this makes this negative, which is bigger than 1 actually. So we still picked decent numbers because I just picked it so far away. But this is no longer happening at 5. This is happening at, I'm going to use my calculator, 2 minus 5 ln of 5 divided by negative ln of 5. So that's at 3.7573. And this first one is 4.3786. 8787, whatever. All right, so that's where I have a max. That's where I'm changing concavity. So I'm changing concavity right before I get to my max, and my max is actually enormously huge. It's way the heck up there. It's like 714. So this is 4 point, oh, hey, stop. 4.378, 379, and 714. By no means would you have to do a problem like this without a calculator. Right, but that is huge. That is way up there. So that means I'm going up here, changing concavity right before I hit it, and then going back down, and it goes concave down forever. So now let's talk about the end behavior on this stuff. And the way that I can do that is I can think about my limits as t goes to negative infinity and the limit as t goes to positive infinity of my function g of t. Right, so if I put in infinity for my positive, that's 5 minus infinity and then 5 times the infinity, so that's negative infinity times infinity, which is why it's going to go to negative infinity. So now it's the other way, though. If I put in negative infinity, right, this would yield 5 minus a negative infinity times 5 to the negative infinity, which would yield 5 plus infinity over 5 to the infinity, which we know this exponential is going to be much, much larger than the linear up top, so this might as well be going to 0. So I know in this other direction over here, this function must come down. Probably comes down rather quickly, but it does go to 0, and it is concave up until this 3.75 number. Well, I drew that way off. But it's concave up until that point. This isn't something that you would have to do by hand. This is very challenging, but this is one that you could use your calculator for as well. Stuff that you would have to do on a test or a quiz for us will be probably more like number 1, where it was all pretty straightforward, all pretty low numbers. I do know that the homework is very challenging for this unit, so you guys can kind of pick and choose as you go through that as well. All right, let's do one more, and then I will be done with you guys, and you can get on to your homework. I believe you are given 2 days for this homework. Yes, and there are 1 through 49, every other one. So is that 50? There's only 25 questions, so if you do half of those, even if you do every other odd, that's probably plenty to get you guys good enough practice on this curve sketching stuff. They do take you some time to get through. I would guess about 10 minutes per question or so. So use your class time, please, please. All right, here we go. So notice I'm only on the interval from 0 to 2 pi. So from my graph here, 0 is right there. 2 pi is 6.28, so I'm only going to be graphing on this interval right there. Okay, so let's find my zeros. And that is something that you would not be able to do without a calculator as well. So, using my calculator, let's see what we got. So negative x plus 2 cosine of x, where is equal to 0. So the first one I get is 1.0298. And that is the only one that is on that interval. Okay, 1 point something. So I'm right there. And f of 0, you can do that without a calculator, because that is just 2. That means I'm starting, let me get rid of my, I'm starting up there. Okay, I'm not going to have any asymptotes. There's no limitations. I'm not going out forever. I'm limiting my domain, so I'm not even going to list or worry about any horizontal asymptotes, especially since cosine kind of goes between, where there's nothing to really state about that. So let's go ahead in and let's do our derivatives. So the first derivative would be negative 1 plus minus 2 sine of x. And this is equal to 0. Would be negative 1/2 So this would be 7 pi over 6 and 11 pi over 6. And I want to relate f prime to f. So let's see, between 7 pi over 6 and 11 pi over 6 would be 3 pi over 2 is a good number. This one I could choose 0, which would be the same as 2 pi. So if I put in 0, it's going to be negative. So I'm decreasing, which means I'm also decreasing out here. 3 pi over 2, sine is negative 1 there, so negative 1 times negative 2 is positive 2, plus 1, this will come out positive, so I'm increasing in between there. So I have a min and a max, as well as a maximum and a minimum on my endpoints. All right, and then our second derivative here will be negative 2 cosine of x, and that's going to be equal to 0 when cosine is equal to 0. So x is pi over 2 and 3 pi over 2. And if I test those points, oh, this one is so much nicer than that last problem. I like trig functions. They're good. They're good. All right, so I can test 0, which same thing as 2 pi, and then I will test pi in between there as well, relating f double prime to f. So if I put in 0, that will come out negative. So that means that comes out negative, so I'm concave down, and then pi would be when cosine is negative 1, so this will come out positive, which means I'm concave up. So I do have points of inflection at pi over 2 and 3 pi over 2. So let's see, pi over 2 is 1.57. And at 7 pi over 6 and 11 pi over 6, I have max and mins. 7, 6 is a little bit more than 3. So I'm going to say somewhere down there. That's probably not negative 2, but I'm going to say it's somewhere down there. 11 pi over 6 would be a little bit less than that, so somewhere in here. And I'm changing my point of inflection at pi over 2, which is 1.57, and 3 pi over 2, which is 4.5, somewhere in here. So let's see, I need to be concave down. Nope, that's a straight line. Come on, Notability. All right, so I have to be concave down all throughout there. And then it goes concave up. And then it goes concave down again until I reach the end. And that would be our best approximation for that graph as we keep going. Yeah, we could find the maxes and mins. I'm not too terribly worried about it on this one, though. Right, because you would just plug in 7 pi over 6 and 11 pi over 6 into your original function to figure out where they are happening. All right. Other than that, I think 40 minutes is plenty long enough for a notes video. Any questions that you guys have on 4.6 though, please let me know. There's a lot going on here, but it's really just kind of seeing how everything interconnects together to help us figure out what's going on with functions. All right, I will talk to you all soon.